Okay, let's look at the assignment. Why do atoms combine to form compounds? You know, when you look out in nature, you tend to not find atoms living alone. They're usually combined with other atoms, usually of different elements, to form compounds. Why do they do that, and what happens when they do that? We're going to look at that in this activity, this assignment. So when you're looking at this, you'll need to make sure that you see that there's a periodic table on the back. The periodic table on the back has a stair-stepping line. We'll look at what that's for. But we're going to begin by focusing on one particular group of elements. The group of elements we call the noble gases. They're the elements that are in this group 18 on the periodic table. Helium, neon, argon, krypton, xenon, and radon. Now the reason why we call them noble gases, one, the gas part is because they're all gases at room temperature. Helium, you know, we use to fill up balloons. Neon, we put in tubes to make neon signs. Argon, krypton, xenon is one that these are making flash bulbs. Radon is a gas that you don't want to come in contact with because there's a radioactive form which, when you breathe, can cause cancer. But they're all gases. But what makes them noble? Now, what makes them noble is when you think about what noble means. It means like you're the king and queen. You don't mix with the common folks. You keep to yourselves in your little kingdom. Well, the elements on this side of the periodic table, likewise, do not combine, except under very rare circumstances in the laboratory, with the other elements on the periodic table. They keep to themselves on this side of the periodic table. They don't react with other ones. We say that noble gases are inert or unreactive. Now, what it is that makes them unreactive has to do with their electron configurations and their electron orbitals. So what we'll look at next is what features they have in their electron orbitals. So if you turn to the front of the assignment, what we'll start with is writing out the electron configurations for the noble gases. We'll just write out the first few, and then we'll see that there's a pattern, and we'll continue the pattern to do the other ones. So the first one, helium, it has 2 electrons, so that one's easy to do using the orbital filling guide. Those 2 electrons go into the 1s orbital, and since there's just 2 electrons filling up that orbital, its electron configuration is 1s2. Easy, easy. Neon is 10 electrons, so its first 2 electrons will go into the 1s orbital, and then the next 2 electrons can go into the 2s orbital, and then there are 6 more electrons that can fill up the 2p orbitals. That makes 10 electrons. And for argon, we have 18 electrons, so we'll fill out 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. That's the 18 electrons for argon. Krypton with 36 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. That should be 36 electrons. Now we're not going to do xenon and radon just yet, but first I want to establish that there's a pattern here, and it's a pattern in what we call the valence electrons. The valence electrons are the ones that are in the outermost part of the atom, the ones that are on the fringe, the outer skin. When 2 atoms join together, it's like shaking hands. It's their outer parts that come together and touch. The outer parts, we can tell which ones those are by looking at their electron orbital configurations, looking at the numbers in front. Those numbers tell us the energy level or relative size of the electron orbitals. The bigger the number, the bigger the relative size of the electron orbital. So the electron orbitals that we're going to look for, the valence electron orbitals, those are the ones that are on the outside of the atom. They're the biggest ones. So when I look at each one of these, I'm going to underline the biggest electron orbitals, the ones that have the biggest energy level number. Those electron orbitals we call the valence electrons. They're on the outside of the atom. Those are the ones that are going to be involved in the chemical reactions. So when we look at those electron orbitals, let's see that there's a pattern. 1s2, 2, 3, 4. If you continue that pattern for xenon and radon, without writing out all their electrons, we could predict that it'll be 5s2, 5p6, 6s2, 6p6. Those will be the outer valence electron orbitals for those elements. And count them. Count how many electrons there are. For helium, There are 2. But for all the other ones, there are 2 plus 6, always 8. 8. 8 is an important number in what we're going to be doing today. The reason why the elements that we're looking at, the noble gases, are relatively stable is because they have completely filled their valence electron orbitals with either 2 electrons or 8 like the other ones. Helium only has an s orbital with 2 electrons, so it is completely filled with those 2 electrons. But the other ones, neon, argon, krypton, xenon, and radon, they have outer s and p electron orbitals which can hold 8 electrons. We call this the octet rule, that 8 outer electrons completely fill the s and p orbitals of these gases. When they're stable like this, they tend not to react with other elements because they have already filled their outer electron orbitals with as many electrons as they can get. And just like the kings and queens, they're not trying to give it away. They don't need any more, so they stay by themselves in their little kingdom on the group 18 part of the periodic table. These elements don't react with the other elements so much. That's useful for some properties of these elements. For example, argon, which is used to fill up bags of food. I'm not sure if these nil wafers are packaged with argon. I'll have to taste them later and see how fresh they are. But the reason why they use the noble gases like argon to fill up bags of food is because they're not reactive. They're inert. Gases like oxygen, which are part of the air that we breathe, about 21% oxygen. Oxygen is a very reactive element and it causes your food to spoil. So if you can get rid of the oxygen in the air inside the package, then you can prevent spoilage of your food product and it'll last longer if people buy it. So noble gases, they are inert and unreactive. And the reason is because they have completely filled outer electron orbitals. Like helium with its 2 electron orbitals, 2 electrons filling its outer orbital, or the other ones with 8 electrons filling its outer orbitals. All the other elements on the periodic table are trying to get like the noble gases. They're trying to get 8 outer electrons. When you look on the back of the periodic table for your assignment, you'll see a stair-stepping line. The stair-stepping line divides the elements into 2 basic groups. Those that are on the left side we call metals, and those that are on the right side we call nonmetals. That includes the noble gases. The ones that are touching the line, except for aluminum, are considered metalloids. That means that they have properties of both metals and nonmetals. When you think about metals, think about things that you're familiar with. They tend to be shiny, they conduct electricity, you can bend them without breaking. They mostly are silver in color, except for a few like gold, copper, and bismuth. The nonmetals over here, they tend to be very different. Many of them are gases. They have a variety of colors. Chlorine is green, bromine is brown, iodine is brown also. Sulfur is yellow, phosphorus can be red, carbon is black, but many of them are gases at room temperature. And the ones that are solids, like sulfur, they tend not to look very metallic. They tend to look very glassy. And instead of bending, they shatter and break in that way. So nonmetals and metals are very different. The nonmetals don't conduct electricity like metals do. The metalloids, the ones that are right on the border, have properties of both. The properties that we're going to be interested in are what happens to them when they interact with each other to form compounds. Now, all of the other elements on the periodic table are trying to get like the noble gases with 8 outer electrons. They want to have filled outer electron orbitals, or 2 like the ones that are trying to get like helium. And in order to do that, elements that are metals, they react by losing electrons. So there's a rule of thumb that will follow that metals will lose valence electrons in order to get 8 outer electrons or 2 like the noble gases. The nonmetals, over on this side, they do the opposite. Nonmetals react by gaining electrons. They'll gain electrons until they have 8 outer electrons like the noble gases and become stable. Metalloids, the ones that are on the boundary, they do both. They can gain or they can lose electrons depending on who it is they're reacting with. So what we'll look at in our examples is what happens to the atoms when they gain or lose electrons, and what happens to the balance of the charges in the atoms. What happens when they become ions? Okay, we're going to work on some examples, and in the examples we're going to follow several steps. The steps are listed, and then below there are some templates on which we'll do the steps. So you can see what the step is about, and then here we'll show what happens when you follow those steps. We'll do 4 examples together, and then we'll look at the problem sets. Now the first problem that we're going to do is for the element magnesium. So I'll write magnesium here. And I'm going to look at the periodic table for magnesium and find it right here on the periodic table. And I'm going to look for its atomic number. The atomic number for magnesium is 12. I need to know that because it counts how many protons there are in the nucleus. There are 12 protons. Protons have a positive charge, and there are the same number of electrons in the space outside the nucleus. There are 12 electrons. The number of positive and negative charges in the atoms on the periodic table are opposite but equal. That means if you add them together, they balance out to 0. That means that there's no charge on the atoms the way that they're written on the periodic table. When atoms gain or lose electrons, those charges become unbalanced. There might be more positive charges or more negative charges, and as a result the atom becomes an ion with a certain amount of charge. And understanding those charges helps to understand the way that atoms join together to form chemical bonds, which we'll look at later. So let's write out the electron configuration for those 12 electrons. So 1s2, 2s2, 2p6, 3s2. Is that 12? That's 10, 12. Okay, so those are the 12 electrons in magnesium. And we'll identify which are the outermost or valence electrons. Those are the ones that have the biggest energy level number. So there are these valence electrons. There are 2 valence electrons in magnesium. The next step is we'll decide if it's a metal or a non-metal or a metalloid. Magnesium is clearly a metal. It's on the left side of the stair-stepping line. So it is a metal. And metals react by losing electrons. So it's a metal, loses electrons. How many electrons is it going to lose? Well, it's going to lose its valence electrons. It has 2 electrons, 2 valence electrons, so it's going to lose 2 electrons. Now when it loses those 2 electrons, what is the remaining largest electron orbital? Well, if we take away the 3s2 electrons and we look at the biggest energy level numbers, 2 is the biggest energy level number, 2s2, 2p6, those are going to be the biggest electron orbitals, 2s2, 2p6, and if you count up how many electrons it is, that's 8 outer electrons. And which noble gas is it that looks like that? Let me find my thing here, 2s2, 2p6, that's neon with 8 outer electrons. So it's going to react and it's going to look like neon. Now the element isn't going to look like neon, just its electron configuration. It's still magnesium. The 12 protons define that as the magnesium element. Chemical reactions don't touch the nucleus. The nucleus is an important part of the reactivity of elements, but protons and neutrons in the nucleus are not gained or lost during a chemical reaction. Only electrons. Chemical reactions are about exchange of electrons between atoms. Okay, now that we've exchanged some electrons, we started with 12 protons, and we had 12 electrons, but we lost 2 of them, so now we only have 10 electrons. And so the balance of charges here, there's more positive charges than negative charges. We have 2 more positive charges. We'll say magnesium is an ion with a 2+ charge. Let's try another example for a different element. The next element we'll do is aluminum. So I'll write aluminum here and find it on the periodic table. Aluminum is here along the stair-stepping line. It's the only one touching the line that's not a metalloid. Aluminum is a full-on metal, and its atomic number is 13. So I'll write 13 protons, 13 electrons. Charges are opposite and equal. And write out its electron configuration. 1s2, 2s2, 2p6, that's 10 electrons. 3s2, 3p1. Okay, now let's identify which are the outermost electrons. The valence electrons are in the energy level, the third energy level, the electron orbitals with the largest relative size. The bigger the energy level number, the bigger the relative size of the electron orbitals compared to the other orbitals. So, these are the outer electron orbitals. These are the valence electrons. There are a total of 3 valence electrons. So the next step is it a metal, non-metal, metalloid? So again, since it's right there on the left side of the stair-stepping line, aluminum is a metal. So it's a metal, and metals react by losing electrons. How many electrons does it lose? Well, it loses its valence electrons, and there are 3 of them, so it's going to lose those 3 electrons. Loses 3 electrons. Now if I lose those 3 electrons, then the largest electron orbitals, the ones that have the largest energy level number, will be these, because their energy level number is 2. So the largest electron orbitals will be 2s2, 2p6, and that is a total of 8 electrons. And like we looked at before, the element that has the same outer electron or valence electron configuration is neon. 8 outer electrons. So it's going to look like neon in its electron configuration when it's done exchanging electrons with other elements to become stable. So let's check out the charges. If we had 13 protons and we had 13 electrons to start, but we lost 3, that means there's only 10 electrons now, 13 minus 3. And the balance of charges, there's more positives than negatives. There's 3 extra positive charges. So aluminum makes an ion with a 3 plus charge. Okay, the next example that we'll do, let's try a nonmetal. Let's try chlorine. So when I look for chlorine on the periodic table, it's on the nonmetal side. It's right over here. It has 17 electrons. So 17 protons, 17 electrons. And I'll write out its electron configuration for those 17 electrons. 1s2, 2s2, 2p6, 3s2, 3p5. Let's count it up. 10, 12, 17 electrons. And the electrons that are in the largest orbital, the largest orbitals are in the third energy level, and so those are my valence electrons. There is a total of 7 electrons altogether. 7 valence electrons. And when I see where it is on the periodic table, I see that it's on the right side of the stair-stepping line, so that designates it as a nonmetal, and nonmetals react by gaining electrons. Non-metal gains electrons. How many does it gain? Okay, well, let's see. We've got 7 valence electrons, and what the elements are trying to do is get 8 outer electrons like the noble gases, or 2, the ones that are trying to get like helium. So in order to have 8 outer electrons, if you already have 7, you only need 1 more to make 8. So it's going to gain 1 electron to make 8 outer electrons. Now if it gains 1 more electron, it's going to gain it to right here. So it would end up 3s2, 3p6. 3s2, 3p6. All the action is going to be out there with those s and p valence electrons in these examples. And if I have 8 outer electrons like this, 3s2, 3p6, then which noble gas electron configuration will I look like? I will look like argon with 8 outer electrons, 3s2, 3p6. So we'll have 8 like argon. Check the balance of charges. If I started with 17 protons and I had 17 electrons until I gained one more, so 17 plus that extra 1, 18 electrons now, the balance of charges is now more negative charges. There's one extra negative charge. So now chlorine has a 1 minus charge. Now, here's a question. Where did that electron come from? Well, maybe it comes from one of those other elements that's trying to lose electrons. Like when aluminum loses its 3 electrons, where do they go? Maybe one of those electrons could go to an atom of chlorine that's becoming an ion. And then maybe another one could go to another atom of chlorine, and so on, until chlorines have gotten the electrons they want, and aluminum has gotten rid of the electrons it's trying to lose, and then everybody's stable like a noble gas and is like a king or queen on the periodic table. That's how chemical reactions work. Let's look at another example. In this one I want to show you something to watch out for. There are other things going on that we're going to ignore. We're just going to focus on one part of the problem for these examples. Our last example is for, which one is that? Nickel. Okay, so nickel. Nickel on the periodic table, right here, element number 28. So 28 protons, 28 electrons. And I'll write out his electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 2, 3d8. That should be 28 electrons. Let's count 2, 4, 10, 12, 18, 20, 28. Now, the biggest electron orbital here, the one with the highest energy level number, is in the 4th energy level number. So here are the valence electrons. There are 2 valence electrons. And it's a metal because it's on the left side of the stair-stepping line. And if you're familiar with nickel, it's shiny and silver and conducts electricity. So it's a metal and loses electrons. And which electrons it loses are its valence electrons. So it's going to lose these 4s2 electrons. So it loses 2 electrons. Now, when it loses those 2 electrons, the biggest electron orbitals are going to be in the 3rd energy level. And we've got s, p, and d electrons in the 3rd energy level. So which ones are we going to focus on? We're just going to focus on these s and p electron orbitals because those are the ones that are shared with the noble gas electron configurations, and because what happens with d electron orbitals, that can get a little bit complicated. It depends on the element that you're looking at and some other rules that are beyond what we're going to look at in just these examples. So when we're working out these examples and problems, just focus on those s and p electron orbitals, and the d electrons, we're just going to put those aside for now for another discussion. So, if we lose those 2 outer electrons, and we focus on the s and p orbitals that remain, then the electron orbitals that we're going to look at are the s and p, 3s2, 3p6 electrons. Those 8 outer electrons are the same electron configuration ending as which noble gas? I've got all these papers here. Argon again, 3s2, 3p6. So it will look like argon. And what will be the charge? Since we had 28 protons to begin with, and we have 28 electrons, but lost 2, now we have 26 electrons. The balance of charges, there are 2 extra positive charges, so nickel makes 2 plus charge. Now, while you're working out the problems, you'll find that there are 6 more problems on the next page. And as you come to a result, here are the problems. As you're working out these 6 problems, when you find a result, you can put the result on this copy of the periodic table, this blank periodic table, and show what charge you found. So locate the element where it belongs on the table, like when we did magnesium. Magnesium is right here on the periodic table, and we found that it had a 2+ charge. And aluminum is right here. We found it had a 3+ charge. And chlorine is right here. We found a 1- charge. And nickel, which is right here, we found had a 2+ charge. Add the charge to your blank copy of the periodic table, and then in class we'll take all of the different results and we'll put them on the blank periodic table on the smartboard and see if there's a pattern. There is an overall pattern to the charges for the ions for these elements that also correlates with the electron orbital endings that we put on this, the periodic table when we made our electron configuration models that are hanging from the ceiling right now. When you go to do the problems, one of your problems is going to be one of those elements that's right on the border. It's going to be one of those metalloids, one of these purple ones here. So let's just, I'm going to pick one and work it out with you. It might not be one that's in your copy of the assignment. Let's just pick out arsenic and look at what to do if you have a metalloid as one of your problems. Okay, arsenic. Arsenic is a metalloid, so I'll use a purple pen. Arsenic has 33 protons and 33 electrons. And if I write out its electron configuration, 1s2, 2s2, 3s6, 3s2, 3s6, 4s2, 3d10, 4p, this is 30, so 3 more electrons. 33 electrons. And identify the valence electrons by looking for the largest energy level number, 4. So these are the valence electrons. There are 5 valence electrons. And it's a metalloid. So it is going to do things 2 different ways. On the one hand, it's going to act like a metal, and it's going to lose electrons. But on the other hand, it could also act like a nonmetal and gain electrons. Depending on who it's reacting with, it could lose or it could gain electrons. So we have to figure this out 2 different ways. How many electrons is it going to lose if it acts like a metal? Well, if it has 5 valence electrons, those are the ones it's going to lose, so it would lose 5 electrons. But if it were acting like a nonmetal and gaining electrons, if it already has 5 electrons and it's trying to get 8 electrons like a noble gas, then it only needs to gain 3 more. If it's losing electrons so that it is acting like a metal, then its outer electron orbitals, s and p orbitals, are going to be in the 3rd energy level. So it would look like this, 3s2, 3p6, and those 8 electrons would be like argon. Or, if it gained 3 more electrons in the 4th energy level, then its outer orbital configuration would be 4s2, 4p6. Those 8 outer electrons would make it look like krypton. So like krypton. So either way, it's going to look like a noble gas by gaining or losing electrons to become stable like the kings and queens on the periodic table. Now let's count the charges. If it started with 33 protons and it had 33 electrons and then lost 5, now it only has 28 electrons with a balance of 5 extra positive charges. By now I'm sure you've picked up that when it loses 5 electrons, the charge that it's going to get is going to be that number, but the other sign. It's going to have a positive charge if it loses electrons. And over here, if it had 33 protons, and it had 33 electrons until it gained 3 more to make 36, I'm sure by now you've picked up also that when you gain electrons, that's going to be the charge, and it'll be a negative charge because we gained more negative charges. Positive charge when you lose negative charges, negative charge when you gain those negative charges. So if I wrote out arsenic, I would write out arsenic, and it could have either a 5+ or a 3- charge, depending on who it's reacting with, if it's being a metal or a nonmetal. If you run into a problem in your problem set that has a metalloid, be careful to make sure to do it both ways for losing or for gaining electrons. And any problems or questions you have, please bring them to class, to homeroom, to lunch, or let me know when you're going to stop by and we can try to figure it out. Good luck.